The C chart is a control chart for monitoring the number of defects per unit or subgroup. In this lesson, we calculate the control limits, create and interpret the control chart. And hello again to this lesson, which essentially has two learning objectives. At the end, you should be able to calculate the control limits for a non-interference probability of 99.73%. And you should also be able to use this knowledge to create a control chart and interpret it. This lesson is divided into two chapters. In the first chapter, we will calculate the control limits for a non-interference probability of 99.73%. And in the second, we will enter this limit into the control chart and discuss how it should be interpreted. This picture shows the relationship between the various characteristics and the control charts used. The different characteristics are shown on the left and the different control charts on the right. The quantitative characteristics, shown on the left, can be divided into two different categories. First, the variable characteristics. These are all characteristics that can be measured. They always have a value and a unit. Examples of this would be the length, hardness, weight, surface roughness, or tensile strength of a component. But we don't want to go into detail about them here. Second, there are the attributive characteristics. Those are all characteristics that only can be counted. On the right side, we have the different control charts for attributive characteristics with a white and yellow background. As you can see, there are 6 control charts for attributive characteristics. As already mentioned, this is about the C chart for the number of nonconformities. Let's start with the calculation of the control limits. When building, for example, pipelines or ships, components are connected with sometimes very long and many weld seams. Various defects can occur in the weld seam. These defects are, for example, incomplete penetration, porosity, or incomplete fusion. In order not to have to check hundreds of meters of weld seam, individual sections can be randomly checked to draw conclusions about the quality of the welding process. For example, sections of 2 meters each could be selected. Such a section would then be a random sample. 10 such sections would be a sample size of K. These numbers are from the example from the table on the right. Upon checking these 10 sections, the following defects were found, from C1 to C3. 9 times incomplete penetration, 6 times pores, and 7 times flank binding defects. A total of 22 defects were found. For the calculation of the control limits, the average number of defects per section, this would be the sample, is required. This C bar is calculated from the quotient of the sum of the number of individual defects and the number of samples. The 3 before the square root in the control limit formula is the quantile of the standard normal distribution for a 1 minus alpha non-interference probability of 99.73%, so plus minus 3 times sigma. With the values given in the table, an average number of defects per weld segment of 2.2 is calculated. With this value for C bar, an upper control limit of 6.67 defects is calculated for one sample. A negative value results for the lower control limit. In such a case, the lower control limit does not apply. Why wasn't the calculated upper control limit of 6.65 rounded up to 7? By rounding down to 6, the conscious decision was made to go towards a 99% probability of non-interference. The probability of a limit violation is then closer to 1 rather than below 0.27%. The control shot, therefore, signals an out-of-control process a little earlier or more frequently. Now let's move on to the creation and interpretation of the C-chart. In the control chart on the right, the number of defects, C, in a sample is plotted on the y-axis. The x-axis scale is for the sample number. In our example, these are the 2-meter-long welding sections. The center line is C bar at 2.2 and the upper control limit, UCL, at 6. The values in the graph are the number of defects on which our example is based. The formula used here for the control limits is designed in such a way that the non-interference probability is 99.73%. This means that there is a 99.73% probability that all values will lie between the control limits. Since we deliberately rounded off the result, this probability is closer to 99%. It's relatively irrelevant whether the probability that the control limit will be exceeded is 1% or 0.27. Crucial here is only that this is a very rare event. Should such an event occur, then this is an indication that the process might be out of control. Then the cause of this event must be identified and the process should be readjusted. Well, that was a lot of new information. Therefore, I would like to conclude by repeating the 3 most important key messages. The control limits of the C-chart for number of nonconformities is calculated using the normal distribution. The non-interference probability in the process is 99.73%. This is equal to the Six Sigma range. 1 or more values above the upper control limit is an indication of an out-of-control process, which may then have to be readjusted. If you found this lesson helpful, please let me know and leave a comment. Thank you for that, take care, and see you next time. Bye.